Welcome to The Explainer. Today, we're diving into the fascinating, incredibly high-speed world that's operating right inside your devices as we speak. Think about a busy, one-lane intersection in the middle of a massive city. You've got hundreds of cars desperate to get through, but obviously only one can pass at a time. Well, your CPU operates in the exact same way. It's a single, incredibly fast lane, and we need a rock-solid system to manage all that traffic without causing a massive pileup. So, ask yourself, how exactly does your smartphone, your laptop, or even the computer inside your car avoid total chaos? When you're listening to a playlist, downloading a file, and typing an email all at the exact same time, how does the system juggle hundreds of background apps without just instantly crashing on you? The answer is our ultimate traffic cop, officially known in the tech world as the scheduler, or sometimes the dispatcher. This is a highly specialized piece of software sitting right at the core of the operating system's kernel. Its sole responsibility, literally its prime directive, is determining exactly which task gets to use the CPU at any given microsecond, making absolutely sure the most important work gets done first.
Okay, let's dive right into this. Here's our mental roadmap for the explainer. First, we'll meet the CPU traffic cop. Second, we'll break down the 3 scheduler types. Third, we'll compare preemptive versus non-preemptive setups. Fourth, we'll explore some popular scheduling algorithms. And fifth, we'll wrap up with real-time system schedulers.
All right, section 1. Let's meet the CPU traffic cop and cover the basics of scheduling. Before the scheduler can actually make any decisions, it has to know the exact status of every task trying to cross that CPU intersection. You see, a process doesn't just magically execute out of nowhere. It moves through a really strict life cycle. First, it's created, and then it enters what we call the ready state. Think of this exactly like a car pulling up to a red stoplight. The engine is on, the driver's ready, but they just have to wait. When the scheduler finally gives the green light, the task moves into the running state and actually gets to use the CPU. Now, if it suddenly needs to wait for something else, like, say, user input, it gets pulled over into a blocked or wait state until it's ready to go again. Moving on to section 2, the 3 scheduler types. Because, even our traffic cop has bosses. Scheduling is actually a massive team effort, breaking down into 3 distinct management levels. Our CPU traffic cop is fast, sure, but it has managers above it controlling the broader flow of traffic. On the slower end, we have the long-term or job scheduler. That's the big boss deciding which processes are even allowed into the system's memory to begin with. Then, stepping it up a bit, the medium-term scheduler handles swapping, basically temporarily moving suspended processes out to a hard drive to free up RAM. But the absolute star of our show is the fastest of the bunch, the short-term CPU scheduler. This one is lightning fast, making split-second decisions to pick from the ready queue and dispatch the CPU to the next lucky task. Section 3. Preemptive vs. non-preemptive. Let's talk about the rules of the road. So when a task finally gets the CPU, how long does it actually get to keep it? Well, this comes down to 2 major philosophies. In older, simpler, non-preemptive systems, a task basically just keeps the CPU until it voluntarily decides to yield it. But in modern systems, we use the preemptive imperative. Imagine you're driving through a one-lane intersection, and suddenly an ambulance with its sirens blaring comes up right behind you. You have to pull over immediately, right? That is preemption. If a critical, high-priority task suddenly becomes ready, the scheduler ruthlessly interrupts the low-priority task and hijacks the CPU. But how does this interception actually happen in practice? It's a precise 4-step dance. First, a piece of hardware, let's say your network card, triggers an interrupt service routine, or ISR. Second, that ISR does the absolute bare minimum processing required and signals a critical event. Third, the kernel jumps in and forces a context switch, completely saving the state of whatever was just running. And fourth, the urgent, high-priority task gets the CPU and executes immediately and deterministically. Now, what's really fascinating about this sequence is what happens exactly when the high-priority task finishes its critical work. The CPU drops straight back down to resume the low-priority task exactly where it left off. And I mean exactly. The low-priority task literally has no idea it was even interrupted. It is incredibly seamless. That brings us to Section 4, Popular Scheduling Algorithms. How do we decide who actually goes first? If preemption is the rule, how does the scheduler establish the hierarchy? How does it choose who goes next when a dozen tasks are all waiting at the red light? Well, they use highly optimized algorithms. 2 of the most foundational ones are first come, first served, and shortest job first. First come, first served, or FCFS, is exactly what it sounds like. It's basically a grocery store checkout line. It's fair, sure, but if a massive task gets in front, everyone else waits forever. Shortest Job First tries to fix this by prioritizing the quickest tasks to just get them out of the way. But there's a huge catch here. The scheduler has to somehow magically know exactly how long a task will take before it even runs, which, let's be honest, is often completely impossible in the real world. Because of those real-world limitations, a lot of systems rely on priority scheduling. Under this model, every single task gets a VIP ranking. Usually the lowest number means the highest priority. It is fantastic for making sure your system responds instantly to critical things, like a touchscreen tap. But the downside? It's terrifying. It's called starvation. If a constant flood of high-priority tasks keeps arriving, your poor low-priority background tasks might literally sit there waiting indefinitely, completely starved of CPU time.
So how do we solve the starvation problem, especially among tasks that share the exact same priority level? Schedulers use this really beautiful concept, the round-robin clock. Instead of one task just hogging the lane, every task gets an equal, fixed time slice, which is also known as a time quantum. The scheduler literally goes around in a circle, giving task A a few microseconds, then task B, then task C, and then boom, right back to A.
Following the logic here, a task gets the CPU. If its total required execution time, its burst time, is less than the time quantum, it finishes up and leaves. Easy. But if it needs more time, the very millisecond that quantum expires, the scheduler ruthlessly cuts it off, pauses it, and cycles it straight back to the end of the ready queue to wait its turn again. It really is the ultimate equalizer. Finally, Section 5. Let's look at real-time system schedulers and the incredibly strict rules of an RTOS. So the crucial point is, when we apply these concepts to critical embedded devices, we're talking pacemakers, anti-lock brakes, industrial robots, we enter the world of real-time operating systems, or RTS. In an RTS, missing a deadline by even a single millisecond could be absolutely catastrophic. Everything must be mathematically predictable. Mapping this out, if 6 completely different processes arrive at different times under a strict round-robin algorithm with a time quantum of 2 units, you can mathematically trace process 1 running for 2 units, getting paused for process 2, and so on, creating this perfectly interleaved sequence of execution taking exactly 21 time units. Because we can map it out so deterministically, we can calculate the exact performance of the entire system. For that 6-process sequence we just looked at, the math proves the average waiting time across those processes is exactly 7.33 time units. In a real-time system, engineers literally rely on this exact, definitive math to guarantee that critical processes will absolutely never be starved. And to lock in those guarantees, an RTOS often uses advanced frameworks like rate monotonic scheduling, or RMS. This is such a brilliant static policy. It basically looks at how often a task needs to run, its period. The rule is incredibly simple. The shorter the period, the higher the priority. If a task has to run every 5 milliseconds, it automatically outranks a task that runs every 50 milliseconds. It mathematically bounds the CPU utilization, guaranteeing total system stability. It really is a masterclass in high-speed organization, which leaves us with this final thought. As you experience this explainer, your own device's traffic cop is frantically waving its arms behind the scenes, preempting tasks, enforcing time quantums, and making literal millions of microscopic decisions every single second. So how many invisible context switches do you think your smartphone executed just in the last 10 minutes? The answer is easily in the hundreds of thousands. Keep wondering about the incredible high-speed systems hiding right inside your pocket.